Dear friends, Aspirants is a collective of mathematics students, research scholars, and teachers all over India, initiated by myself in the year 2017. And we used to arrange online problem solving sessions and online test series to help the students who prepare for different national level competitive examinations. As a part of that series, today we have Dr. Priyambada Tripathi is with us. She is currently an assistant professor at Dyal Singh College, University of Delhi. Dr. Priyambada did her PhD from Delhi University with the CSIR JRF, and she did post-graduation MSc from Banaras Hindu University, and her BSc was from Tripathi College, Varanasi. Dr. Priyambada is associating with math aspirants long back. Last year, she had engaged a career session platform. So I am very happy to introduce Priyambada to all of you. And I hope that today's session will be really helpful to understand the ideas and concepts regarding Riemann integration, which is one of the important topic for competitive examinations. So I welcome everyone to this program. Welcome, Priyambada.
Thank you, sir. I'm happy to be a part of this association again. It's my pleasure to present something of Riemann integration. So I hope the talk will be beneficial to the participants. Okay, so I was just talking about the concept of Riemann integration. So it's very important to understand the concept of Riemann integration. Then only you can solve the problem, because without understanding the concept of Riemann integration, you cannot proceed for the problem solving. And also because this Riemann integration is the very updated part of the real analysis course, so we must present some glimpse of some part of the real analysis, which is very important part we are going to use in the Riemann integration. So I will start my lecture with some introductory things which we are going to use in the Riemann integration. So I'm going to present my screen. Okay, so actually this topic is very lengthy, so I thought to teach by this self-written already notes, because if I will write, then it will take a lot of time. So these are the basic things which we are going to just revise, because I assume that everyone is aware about this. So first of all, what is a bounded above set? And like this, so subset A of the set of real number. So we consider, so what we define a bounded above sets. So everyone is aware what is bounded above set. So first of all, a real number alpha is an upper bound for a subset for A of R if for every element X in A, X is less than or equal to alpha. Then in this case, alpha is called an upper bound for the set subset A, and this subset A is called bounded above set. In the similar manner, we can define the lower bound for the subset A. So a real number beta, which is called a lower bound for the subset A, so that if for every element in A, beta is less than or equal to Y, then in this case, A is called bounded below set. Okay. Now, what is more important in all these things? The negation is more important. Negation and contrapositive, these two important aspects of any statement, which is more important in mathematics, while problem solving part. If we have to solve some questions, if we have to apply something, the negation part, it is very important to understand the negation, and it is very important to how to apply the negation and how to apply the contrapositive part. So if A is not bounded above, what do you mean by that? So if A is not bounded above, that means A has no upper bound. So how to state it mathematically? These are a few things we need to know before the starting of the Riemann integration. So what is the definition for the bounded above set and upper bound? So for every element X in A, X should be less than or equal to alpha. Suppose alpha is not an upper bound for the set A, then what will happen? Then what will happen? What is the negation of this, particularly this thing? What is the negation of this thing? So negation of this thing will happen that there exists some element in A such that x is not less than or equal to alpha. Okay, so that's what I have written. So there exists an element z from A such that z is not less than or equal to alpha. So what do you mean by that? If I say z is not less than or equal to alpha, so by trichotomy law we know that there are three things between two real number. A is less than B, A is greater than B, or A equal to B. So if I'm saying that z is a real number, alpha is another real number, if z is not less than or equal to alpha, then what else we are left with? So we are left with z will be strictly greater than alpha. So if there exists an element z in A such that z is strictly greater than alpha, then in that case alpha will not be an upper bound. And similar logic goes with lower bound also. Now one can observe that there are infinitely many upper bounds and there are infinitely many lower bounds. So we define following the least upper bound. So if A is a subset of R which is bounded above, then a number alpha is said to be least upper bound, or even sometimes we call it supremum also, if this satisfies these two definitions, these two things. So first of all, alpha must be an upper bound of the set A. And if gamma is any other upper bound, then alpha must be less than or equal to gamma. What do you mean by this? This means that alpha must be the smallest upper bound, or in mathematics language, alpha should be the least one. So that means alpha is the least upper bound among all the upper bounds. So that's why it is called alpha. That's why it is called least upper bound. And similarly, we define for the greatest lower bound are called the infimum. Now next comes the completeness property, which is again a very, very important property while doing the Riemann integration. So what is that? Every non-empty subset of real number that has an upper bound also has a least upper bound, or similar thing goes for the infimum also. If any bounded above set we have, then that supremum must exist, or we usually call the least upper bound. This word is more convenient than supremum because least upper bound justify the name itself. So every non-empty subset of real number that has an upper bound, it will have least upper bound. So now, why I'm doing all these things before Riemann integration, why it is important? Because we'll be needing all these things while doing the Riemann integration. So now one more aspect is very important. If we have a non-empty set A and which is bounded in R, then if I take some positive real number A, then A times A, we define a new set A times A by this A times X such that X belongs to A, then what will be the infimum of this newly defined set and what will be the supremum of this newly defined set? So you need to think of these two things. So similarly, you see that the result turns out to be something like this. The supremum of this and infimum of this, what will happen to this? And now when A is less than 0, then what will happen to these results? So supremum of A times A is nothing but A times supremum of A, and infimum of A times A is nothing but A times infimum of A. Okay, now what will happen if A is less than 0? And now another most important result is this: if A is a subset of B is subset of R, then both set I'm taking A and B bounded subset of R, then I want to know what is the relationship between infimum of A and infimum of B, supremum of A and supremum of B. Okay, so if A is a subset of B, then supremum of A is less than or equal to supremum of B, and infimum of A is bigger than or equal to infimum of B. So now all these four we can relate it like this. So this result is more important in Riemann integration while proving many results. So infimum of B is less than or equal to infimum of A, and everyone knows that infimum is always less than supremum. So infimum of A is less than or equal to supremum of A, and supremum of A will be less than or equal to supremum of B. So whenever A is a subset of B, this result is true. Okay, so now suppose now we are defining what is a bounded function. So if we have a function f from some subset D of R to R, then f is bounded above if the set f of D, that is a range set, If range set is bounded above in R, then we see that this function is bounded above. What do you mean by that? If range set is bounded above, there exists some real number B such that f of x is less than or equal to B for every x in the domain D. Similarly, we define the bounded below function related to range of the function, and we define the bounded function. So if there exists some real number R and B such that mod fx less than or equal to B for all x in D, then in this case we say that fx is bounded. So many results are there, and the Archimedes property everyone is aware. So now I'm not going to all those things. Now I'm going to start the Riemann integration. So before starting the Riemann integration, I would like to ask one question to the audience. So Riemann integration, Riemann is the name of the mathematician, right? And integration you have seen already in the school. So can I ask one small question? You have seen the integration and differentiation both in your school, right? So what do you think? Which came first? Integration came first or differentiation came first? Can anyone answer, please?
Integration came first.
Why? Why do you think
Because
so?
initially we use integration to find out the area of non-standard figure.
Okay.
That's why we are using first integration, and then after later on differentiation or related concept is developed by the Leibniz or some
Yeah,
other mathematician.
right. Thank you. Any other opinion? Okay, so I'll move to the Riemann integration concept. So as he suggested that integration came first, so he's very correct actually. So question, so what is the motivation of Riemann integration and how the motivation goes into the subject and growth of the subject? Okay, so we see, let's see. So my question was that integration or differentiation, which one was developed earlier? So many suggestion came like differentiation. Some people said differentiation came first. Some people said integration came first. So now, as everyone knows here, that integration came first. So obviously differentiation came first. This suggestion is not correct. Okay. So let's see. So as he already answered why integration came first. So main idea of integration, what is the main idea of integration? Main idea of integration is to assign a real number A called the area to some region R bounded by the curves x equal to A, x equal to B, y equal to 0 and y equal to fx, where f is non-negative. So basically what is the mathematical projection of this concept? We have a region which is bounded by these curves, and if you want to calculate the area, then this idea comes from this. But in very ancient area, people were aware about the calculating area of rectangle only. Simple planar objects like rectangle, square, and triangle, and many other polygon kind of things. Simple planar objects. So first of all, rectangle is the oldest object for which we know how to calculate the area. So what is the most basic geometric region for which area is known? That is a rectangle. So how to calculate the area of rectangle? Suppose I have rectangle R, then area is L times H. That is a real number. Area is again a real number. You can see that. So now integration was developed much earlier than differentiation. So how to project this concept into mathematical version? So let's see. So we have this rectangle and length. Suppose I took 2 points on the real number A and B. So A is less than B. Then I pick this point A and B and I draw the vertical line and at y equal to C. So I made this rectangle. So my length is B minus A and height is C. Suppose this height is C. Then what is the area? C times this length. This length, C times this length. So this length is nothing but B minus A. So area will be C times B minus A. So basically what is the motivation? Now if we have to calculate the area of any object, like which looks like this, suppose I have some object or some object like this or some object like this. So I want to calculate the area of all these objects. So how to calculate? And provided only what you know, only you know that how to calculate the area of rectangle. So what you will do, so suppose I have this shape, mango shape, and I want to calculate surface area of this mango. So what we do, I just because I know the calculating the area of rectangle, so I will draw some rectangle on this mango, and then so suppose I have many rectangles on this mango, and then I will calculate the area of all the corresponding rectangles. So suppose first of all I have to make the rectangles on this mango. Okay, so you see that there are rectangles for which I can calculate the area. So there are rectangles for which I can calculate, but there are some left area on this mango. This is my left area for which I cannot calculate the area. Okay, this is also left, this one is all, because rectangle is not because this area of mango is not covered by my rectangle. Okay, so you see that if I try to draw the small rectangle on this mango, then I can calculate the approximate surface area of this mango. Okay, but there are some area which are left on this mango. I'm not able to calculate the whole area of this mango. So what we will do, we're just trying to maximize our calculation. We're just trying to maximize how to get the maximum area of this mango, so that this left area will be covered. So what all these things are motivation. So any shape of object, any object of any shape, we can just how to calculate, provided we know only calculating the area of rectangle. We just draw the small rectangle and we calculate the area of all rectangle, and we'll take the sum of all areas of rectangles. So we'll get the approximate area. We may not get the exact area because we can see that many areas, part of areas are not covering by this method. So how to project this concept mathematically? Let's see. So we have a R, the region bounded by x is equal to a, x is equal to b, and y is equal to fx some curve, and y is equal to 0. Then this is some nice picture which is on Cartesian plane. So I have a 2 point, x is equal to a and x is equal to b, and I want to, and this region x is equal to a, this line, and x is equal to b, this line, and this curve y is equal to f of x. So I want to calculate the area of this object. So what we do, so again I'm using the same method. So I want to draw the rectangle. So how to draw the rectangle inside this area? So I pick some point on the x-axis. Suppose I pick 1, 2, 3, 4 points on the x-axis, x1, x2, x3, x4, and by picking these 4 points, I draw the vertical lines, x1, x2, x3, and x4. Now the question is that now we have two kind of heights. So at x is equal to a and x is equal to 1. X is equal to 1, x1 is bigger height, while x is equal to a is lower height. Again, come to x1 and x2, and you see that x1 is upper, means a bigger height, and x2 is lower height. Again, x2 and x3 comparing, you see that x2 is bigger height, x3 is lower height. Again, you see all these things. So there are two categories of heights, lower height and upper height. So which height we should pick for constructing our rectangle? So we will do the things uniformly. In order to do the things uniformly, once we pick the lower height and once we pick the upper height. So in this picture, you see that if you x equal to a and x1, so x equal to a is the lower height. So by picking this height, we construct our rectangle. Now x1, x2, x2, corresponding to x2, the height is lower, so we'll pick this height. And again, x3 is lower height, so we'll pick this height. And here it is x4 is the lower height, so we'll pick this height, and again here it is. So all these area. So whenever we pick the lower height, all these area we calculate and sum it up, all the areas. So this area, by picking the lower height, this area is called. Now again, what is the problem in this method? You see that there are a lot of area which are left. So this is a left area, this is also left area. So we are not able to cover many areas. So how to cover? The problem is that how to cover all these area such that we will get the approximate maximum area of the object. So this is one of the thing, calculating the area by picking up the lower heights. Another thing is that by picking up the upper height. So first of all, how to remove this problem, how to get more into the area of the object. So how to cover up the left area? So suppose I pick one point. Suppose I pick one point between x equal to a and x1. Suppose I pick one point T and I draw a vertical line. Now I can construct again new rectangles. So I'm just taking the lower height. So corresponding to this, at x is equal to T and at x is equal to x1, my lower height is T. So I will pick this rectangle again, and between x is equal to a and x is equal to 2, this x equal to a is the lower height, so my another rectangle is this. So in this way you see that the left area has been reduced. So this part of left area has been covered. So you see that by introducing a new point, again a new point, we can cover up the more of the left area. So what are these things? So let's see. So you see that if we introduce a new point, suppose T1 between x equal to a and x1, again T2 between x1 and x2, we are able to cover up more of the left area. So you see that the area calculated earlier, that has been increased by the indicated circle. You see that this area has been increased. We have covered this area also by introducing new points and new points. So the more finitely many points we will introduce, more area we will cover up. So let's see what is going on. So you see, first of all, we must define something. So lower sum, what is a lower sum? Lower sum is the sum of area of rectangles inscribed inside the region bounded by the graph. So if whenever we pick the lower height and we pick the lower height and we calculate the area of those rectangles and we sum it up, then this area is called lower sum. So because we had only two options, by picking the lower height or by picking the upper height. So now we construct the rectangle by choosing the upper height. So what is the problem we get when we choose the upper height? So you see that in this picture, when we choose the upper height, then we get extra area. So now how to reduce this extra area? The problem is that we want to reduce this extra area to reach the exact area of the planar object. Whatever the object, we want to reach to the area, approximate area of that object. So we need to remove, or we need to reduce this extra area. So how to reduce this extra area? Then again we introduce some more point between any two points. So suppose I have introduced this T1 between x equal to a and x1. Then what we get, you see that by picking this T1, we draw a vertical line and then we pick the upper height. And then what we get, you see that if we draw the rectangle, then this area will be there and this area will be there. And this encircle area will be removed already. In the similar way, if we keep on introducing some more points in this way, then extra area will be removed. So what is going on here? So see, when upper sum is the sum of area of rectangles circumscribed or superscribed the region bounded by the graph. So basically, let me give the overview of the whole things. What we did, we know the area of rectangle, how to calculate. Now we want to calculate the area of any shape object. Okay, so what we did earlier, we draw the rectangles on the planar object, we calculate the area of each rectangle and we sum it up. But whenever we project this concept onto mathematics, in a mathematical concept, then we have this Cartesian plane. We project our object onto Cartesian plane. We draw the rectangle. Now we have two choices. Constructing rectangles by two choices, by picking up the lower height and by picking up the upper height. So in order to make the things uniform, once we pick all lower height and once we pick all the upper height. So whenever we pick the lower height, we are getting the left area. So we want to cover up the left area by introducing more points. Again, what is happening when we are choosing the upper height? We are getting the extra area. So we want to remove those extra area by introducing the more of finite number of points into the interval AB. Okay, so till now, any doubt? So this is a rough idea what we are doing, the motivation of the Riemann integration. Okay, so let's move to next. So now we are going to give the whole things to the mathematical picture. So I'm following the book Elementary Analysis by Ross, and this is from chapter 6. So we define few things, because you see that the concept of lower height and upper height came into picture. So there are so many lower heights and there are so many upper heights, and one assumption we are making here, our function will remain bounded. We are taking that function is bounded. Okay, then this assumption will be throughout the Riemann integration concept. So our function is bounded. So let's see how the mathematical version of these intuitively concept goes on. So the definition number 1, we have, suppose we have a bounded function on a closed interval AB, and for S is any subset of the interval AB, we have a following notation. Based on the lower height and upper height, we have seen we need two kind of height. So capital M of the function f on the subinterval S, we define the supremum of the function on that subinterval S, and the small m, we define the infimum of the function on that subinterval. Now, how to pick the points? Because you see that in order to construct our rectangle, we must pick some point in the interval AB. Suppose we pick some AB interval, then we must pick some points inside AB. So in order to how to pick those points, we define next term, that is called partition. So what is partition? The whole purpose of defining the partition is we want to construct the rectangle, and for constructing the rectangle, we must fix some point on the horizontal on the x-axis. So partition P of AB is any finite order subset having the form. So we name it P, which is defined as, we start with the initial point A, name it T0, and T0 is strictly less than T1, T2, and so on. And the last point is B, that is named by Tn. So suppose there are n points, finitely many points. So in this manner, we will choose our point corresponding to which we have to draw the vertical line and construct our rectangles. So this thing is called partition. So for any k running from 1 to n, tk minus 1 and tk, this denotes the subinterval of interval AB. For k is equal to 1, for example, t0, t1 will be the subinterval. For k is equal to 2, t1, t2 will be the subinterval, and so on. Next thing is important, length of interval. Length of interval is defined by the highest point minus the lowest point. So the bigger one minus the biggest one minus the lowest one. So B minus C will be the length of interval. This is a very simple thing. In the similar way, we can define the length of each subinterval. So suppose I have a subinterval tk minus 1 and tk. So what will be the length of interval? So that will be, of course, tk minus 1. Now, if we have a partition and corresponding to those points, we have a subinterval, and we have defined the length of each subinterval. If we sum the length of all subinterval, we will get the whole of interval, and that turns out to be, so if we sum it up the length of each subinterval, summation 1 to n, tk minus 1, that is nothing but t1 minus t0, t2 minus t1, and so on. That is nothing but b minus a, the length of subinterval AB. Now we define the capital M of the function f on the subinterval tk minus 1 tk. That is nothing but the supremum of the function on this particular subinterval tk minus 1 and tk. Similarly, we define the infimum of the function, that is defined by on this subinterval small m. So infimum of the function on this subinterval tk minus 1 and tk. So why we are defining, I hope you are getting why we need to define this infimum and supremum on each subinterval and of the function, because function is bounded already and these things are existing. And in order to choose our lower height and upper height, so many things are going into the picture. So that's why we are defining these things. And already that's capital M of the function on the whole interval AB, that is supremum of the function on the whole interval AB, is small m, that is the infimum of the function on the whole interval AB. Now the natural question arises that what is the relationship between the supremum and supremum of the function of the whole interval and the supremum of the function on a subinterval. Or similarly for the infimum. So now look at the picture. We have this function. This I have drawn a picture of function, any random function, arbitrary function, y is equal to f of x, and y is equal to 0, x is equal to a is here, x is equal to b is here, and partition is there. So what is the infimum of the function of the whole on the whole interval? That will be the lowest height. So this is an intuitive idea. I'm not doing it, I'm not proving anything mathematically. Just look at the picture and get an intuitive idea what is going on. So small m, that is the infimum of the function on the whole interval. So that must be the lowest height, because function you represent by ordinate, that means by height. Okay, so the small m is the height, that is the lowest height, and the capital M, that is written in the red, that is the highest height. So these two things will be here. And now if you pick any interval, any subinterval, suppose tk minus 1 and tk, on that subinterval, that is a very, very obvious thing. The infimum will be lying here, and maybe infimum will, supremum will be here. So what is the relationship between all these things, all four? So it is an easy observation. First of all, the supremum of the function on the whole interval will be greater than or equal to the supremum of the function on any subinterval for any k. And similarly, the infimum of the function will be the lowest one. So that will be less than or equal to the infimum of the function on any subinterval. Now all these things are introduction and the overview of all intuitive idea. So now we are going into the main, what is going on, what is the integrability. So first of all, although we are the topic is Riemann integration, but before that Darbo introduced the integrability criteria. So Darbo was a French mathematician who gave the basic idea of integrability. So spelling is, you see that DARBOUX, some people call it Darbox, but the real pronunciation, because he was a French mathematician, the pronunciation looks like this, Darbo. Though it does not matter, pronunciation does not matter, but still it is a name of a famous mathematician. So we just be careful. Okay, so in order to, based on the previous discussion, we defined first of all upper Darbo sum, UFP. It is denoted by UFP, U for upper, F for the function, and P for any partition. So P stands for the partition, F is any function for which we are talking about upper sum, and U stands for upper. Okay, so upper Darbo sum UFP of the function F with respect to the partition, because partition can be you can choose partition. There are infinitely many people, they can choose infinitely in many ways. So partition can be anything. So particularly that particular partition, with respect to that particular partition, we define upper sum. So upper sum is defined by the summation k is equal to 1 to n capital M of F on the subinterval tk minus 1 tk times the length of the subinterval. This is simple formula of the area of the rectangle. Okay, so upper sum is the sum of the area of rectangle superscribed the region bounded by the graph of the function y is equal to 0, x is equal to a, and x is equal to b. Suppose I have this graph. I have a function x is equal to a and x is equal to b. Suppose I define a function fx. I define a function. This is alpha 1 when this a to x1. Suppose my point is x1 here, x2 here. Okay, so f of x is equal to alpha 1 when x belongs to a to x1. Now this is alpha 2 when x1 to x2. So x1 to x2, suppose this is some alpha 1 is less than alpha 2, I'm defining it. So this is my alpha 2. And this is alpha 3, h2 to b. So this is my alpha 3. So this height is alpha 1, and this height is alpha 2, and this height is alpha 3. So what is the area? What is the area? Area of, if I want to calculate the area of this function under this thing, so what will be the area? Area of this rectangle plus area of this rectangle plus area of this rectangle. So the length of subinterval, this is the this length of subinterval multiplied by this height, this length of subinterval multiplied by this height, and this length of subinterval multiplied by this height. So in this way, we'll get the area of each three rectangle, and we'll sum it up, and then we'll get the area. So this is nothing but alpha 1 times x1 minus a plus alpha 2 times x2 minus x1 plus alpha 3 times b minus x2. So this is nothing but the upper sum if we are picking up like upper height. So upper Darbo sum is the sum of area of rectangles superscribed. So by taking the upper height. So this is the picture. You see that this is the picture of upper sum. So making rectangles by choosing the upper height. So you see, this is my subinterval, x is equal to a and x is equal to b. These are my points x1, x2, x3, and so on. This is some, suppose xr. So corresponding to these points, I have chosen the upper height, and you see that in this upper sum we are getting extra area. You can see that the red rectangles, the area of all red rectangles will give you the upper sum, and in order to while calculating the upper sum, we're getting the extra area. Now we define the lower Darbo sum. So lower Darbo sum, it is denoted by LFP. L stands for lower, F for function, P for partition. So lower Darbo sum of function f with respect to the partition P, it is summation k is equal to 1 to n small m f tk minus 1 tk times tk minus 1 tk. So this is again the same thing. We are calculating the area of rectangle by taking the lower heights. So now this is the picture of lower sum. We can see that. So you see that I chose my lower height. So these are the left area. You see that the blue arrow indicate all left area. So what are the things like when we calculate the lower sum, we are having so much left area, and when we are calculating upper sum, we are getting the extra area. So how to get the approximate area of the object. So in lower sum, we want to cover up more of the left area. In upper sum, we want to reduce more of the extra area. So these are the simple observation in mathematical observation. The upper sum is nothing but it is given by the summation of this thing, and that will be less than or equal to the supremum of the function on the whole interval AB times this thing. So if this is a simple calculation, so that upper sum is less than or equal to capital M of the function on whole interval AB times B minus A, and similarly the infimum of the function times B minus A, it is less than or equal to lower sum of the function. So by the definition of upper and lower sum, we can make a simple observation, although it can be proved mathematically also. These are the simple observation we are making it. So this box thing, we see the simple observation, the small m of f on the whole interval AB times B minus A less than or equal to lower sum is less than or equal to upper sum is less than or equal to this. Now what is the Darbo integral now? Upper Darbo integral UF, it is denoted by UF, U for upper Darbo integral of the function f. So upper Darbo integral UF of f over any interval AB, it is defined as UF is equal to infimum of all upper sums where P is a partition. So P is any partition. So P can be any partition, it is any arbitrary partition. So many partitions are there. So over all the partition, we get many upper sums, okay? And then UF is defined, upper Darbo integral will defined by infimum of all this. So the natural question is that how can we define this upper Darbo integral? So note that this UF exists. How does this exist? So you see that as per previous discussion, we have seen that with the increase of finite number of points in the partition P, upper sum decreases, and we know that function is bounded because assumption was that function is bounded already. So by introducing more and more points, because partition is arbitrary, there are so many partitions. So by introducing, suppose in one partition there might be number of less points, in other partition there might be different number of points. So there are so many choices for the partition. So with the increase of finite number of points in the partition, upper sum decreases. You have seen that whenever we introduce the points, upper sum was decreased because the extra area we are getting, that has been reduced. That means upper sum is decreasing. And upper sum, which is an area, which is a real number. So we have a set of upper sum which is decreasing, but function is already bounded. So what we have a set of upper sum which is decreasing and bounded. So that means that we have a set of upper sums which is bounded below in R. So now by completeness property in R, infimum of all upper sums, where P is a partition of AB, exists. Then only we are able to define this quantity as upper sum, because this thing exists. Okay. In the similar manner, we define the lower Darbo integral. So lower Darbo integral LF of F over AB is defined by the supremum of lower sum. P is the partition. So again, the question comes into the picture: LF exists or not? So obviously LF exists, because we have seen that with the introduction of finite number of points into the partition, lower sum increases, but function is bounded. So we have a set which is in bounded above. So by completeness property, supremum exists. So LF and UF both exist and both are real number. So now, how we define Darbo integrable function? A function is Darbo integrable on the interval AB if LF is equal to UF. In this case, we denote it A to B F by A to B Fx dx, that is lower integral equal to upper integral. So when lower integral is equal to upper integral, then we say that function is Darbo integrable, and we denote the area of the function under the curve by A to B F. Intuitive area should be approximable from both sides, below and above. So you see in the picture, you see whenever this LF is equal to UF, that means upper sum goes below, because upper sum goes below, upper sum decreases and lower sum increases. So lower sum goes above and upper sum goes below. This is an intuitive area, intuitive idea of the picture. So at this point, the green point, at this green point, both coincide at some number, and that number is called integral of the function. So when LF is equal to UF, we get the infimum and supremum approximately same, and that gives the approximated or required area. Now, in order to grow this subject, we define something, because it's not very easy to define, because there are infinitely many choices for the defining this partition. So we stick to some particular partition, how we define and how to calculate the area. So here this partition P is equal to T0 and B is equal to T1. It is called trivial partition of AB. And number 3 is very important in order to calculate, like you are solving some problem. Then if you are solving Riemann integration, some function is Riemann integrable or not, some function is Darbo integrable or not. Then for any natural number n, we define a point Ti in this way: a plus I divided by n, b minus a. For I is running from 0 to n, then this partition T0, T1, Tn of the partition AB, this will be of equal length or size. We can see that. So this formula is basically we are going to use in order to calculate Darbo integral for many of the function. We are putting the partition of equal size. This will make the things easier. Okay, so any doubt so far? So this was the mathematical version of Darbo integrable. So let's see. Next thing. So let's see some examples. First example, very simple example. If we have a function f from a to b to r, it is a constant function. It is a constant function. F is equal to c for all x belongs to a comma b. find the Darbo integral of this function. So I hope I'm audible, right? No one is asking any doubt, no one is asking any question. So am I audible, sir? Hello? Am I audible?
Audible.
Okay, fine. Okay, so yeah, let's go for the example. So no, I'll be slow down now. Okay. So I have this function, constant function, right? So I want to calculate the Darbo integral for this constant function. So first of all, I will take some partition of the interval AB. So I define this partition P, T0 equal to A, T1, T2, and T and B. It is a partition of AB. So now I have this picture of the constant function y is equal to fx, and I have some partition, and corresponding to those points in the partition, I have drawn the vertical line in order to construct our rectangles. So now because this is a constant function, so rectangles are very clear, right? You can see in the picture. So first of all, in order to calculate the Darbo integral, what we need to calculate the upper sum and lower sum, and then we need to proceed further things. So in order to calculate the upper sum, we need the supremum of the function on the particular subinterval and infimum of the function on the subinterval. So suppose there is some, this is my subinterval, tk minus tk, tk minus 1 tk, and then supremum of the function, it will be, you can see, because this function is constant function, so it will be c itself, and it will be the infimum of the function on that subinterval. And because this is going to be true for all the subinterval, because function is constant. So now you can calculate the upper sum, upper Darbo integral. So summation 1 to n, supremum of the function on this subinterval times length of the subinterval. So because supremum is equal to c, this is c, and now c is a real number, I'll take the outside of the summation. So this is the thing, c times summation 1 to n, tk minus 1, the length of subinterval from 1 to n, all the sum. So as you have seen already, this value is nothing but the sum of the main interval AB. So the length of the subinterval will be b minus a. So the area upper sum is nothing but c times b minus a. Now, in order to calculate the upper Darbo integral, we have to take the infimum of this quantity. Now this quantity is constant quantity, you see that. So upper integral, how to calculate? The infimum of the upper sum. Infimum of the upper sum. So infimum of the c times b minus c. This one is there. In a similar way, if we calculate the lower sum, so 1 to n, infimum of the function tk minus 1 tk times tk minus 1. So this value is same again. You see that because the function is constant, so infimum is nothing but c itself, and the sum of all length of subinterval turns out to be b minus a, the length of interval AB. So what is the supremum of this thing? Supremum is nothing but c times b minus a itself. So from equation 1 and 2, you see that both are same quantity. So from 1 and 2, uf is equal to lf, that is c times b minus a. So we declare that this function is Darbo integrable, and the value of the integral fx dx is equal to c times b minus a. Our next function is that fx is equal to x. Fx is equal to x. So I have taken this interval f from 0 to b r such that fx is equal to x. So now this is, you see, this is a line passing through origin, and our interval is 0 to b, and b is greater than 0. So b is some positive number, positive real number. This is defined on this subinterval. So we have to find the Darbo integral of f. So let's see how to define. So first of all, I have drawn the picture of the function y is equal to fx, that is my x. That is my x, you see that. So now what we do, again, partition is there, t1, t2, and so on, tn minus 1. This is my subinterval tk minus 1 tk. And you see that blue area means by picking up the upper heights, we make I made some rectangle, and by picking up the lower height, I made the red rectangles. So the rectangles covering the blue area, that is upper sum, and rectangles covering the red area, that is the lower sum in the picture. So in the picture itself, you can see that what is the lower sum and what is the upper sum for this particular function. So now we'll see the mathematical thing. Observe that, first of all, in order to calculate the upper sum, we need the supremum of the function on the subinterval. So you see that this function f of x is equal to x. This function is increasing function, right? So corresponding to tk minus 1, value of the function will be tk minus 1 itself, and corresponding to tk point, the value of the function will be tk itself. But we know that this function is strictly increasing. You can see that y is equal to fx is equal to x. This function is increasing. So at this point, tk minus 1 will be tk minus 1, and tk value will be tk only. And we know that tk minus 1 is less than tk. So, and because of the increasing function, f of tk minus 1 is also less than f of tk. So on this particular subinterval, tk minus 1 tk, what will be the supremum of the function? F of tk only. That will be tk, because tk is the highest height corresponding to this highest. Tk is the point, that is the greatest point in this subinterval. Tk minus 1 tk. Tk is the biggest point, and corresponding to tk, f of tk is the highest height in this subinterval, and tk minus 1 is the lowest point, the smallest point in this subinterval, and corresponding to this point tk minus 1, f of tk minus 1 is the smallest height. So the infimum of the function will be f of tk minus 1, and supremum of the function on this subinterval f of tk, and infimum will be this. So f of tk is nothing but tk, f of tk minus 1 is nothing but tk minus 1, because f is increasing function and so on. So now how to calculate the upper sum? Just putting the value in the formula. So summation 1 to n f of tk minus 1 tk times length of subinterval. So now what is the supremum? That is tk and length of subinterval. Similarly, the lower sum, what is the infimum of the function tk minus 1 and the length of subinterval. Now we need to decide what is the partition. So again, as I told you that equal size partition is the best partition in order to solve any problem. So I'm doing it by using this equal size partition. So my partition is that first point in my B 0 and last point is B. So my partition of 0B of equal size is tk will be kb divided by n by using this formula. I told you earlier, ti for any I will be the value a plus I times b minus a divided by n. But my a is 0 and b is b. So a key, the value of a, we have put this 0, and then we'll get ib divided by n. And for any k, tk value will be k times b divided by n. So now I'm going to put the value of tk and tk minus 1 in this upper sum and lower sum, and we'll see what is the value we are getting. Upper sum is nothing but summation 1 to n. Tk, the value of tk is nothing but kb divided by n, and this is tk minus 1. So we have put this value, k is some. So after calculating all these things, we got this value, and ultimately we got this value. So b is some constant value, b square divided by 2 times 1 plus 1 by n. Now you see that for the larger value of n, this whole thing goes to b square by 2. So upper sum is nothing but it is approximated as b square by 2, and lower sum in the similar way, after putting the value of tk minus 1 and tk, we will get for the larger value, it is also approximated by b square by 2. Now in order to calculate Darbo integral, we must calculate the upper integral, the upper Darbo integral and lower Darbo integral. So upper Darbo integral is calculated by the infimum of the upper sum. So because it is the infimum, so it should be less than or equal to any of the upper sum. So upper sum has been calculated by approximated by b square by 2. So the infimum of upper sum will be less than or equal to b square by 2 by the definition of the infimum. And similarly, lower integral will be calculated by the supremum of the lower sum, but lower sum has been approximated by b square by 2. So the supremum will always be bigger than or equal to any of the lower sum. So it will be greater than or equal to b square by 2. So now from equation 1 and 2, we can see that b square by 2 is less than or equal to LF And we know that lower integral is always less than or equal to UF. We will also prove it by using the mathematical thing. So this is happening. So this gives you that LF is equal to UF is equal to B square by 2. That is the integration of the function fx is equal to x from 0 to b. So you must have seen in a school 0 to b x dx. Simple integration you can do x square by 2, 0 to b. This is nothing but b square by 2. But now you see that by Darbo integrability, you have calculated this value. Similarly, you have to calculate the fx is equal to x square. So I'm not going to explain this thing. Again, by using the equal size partition, this is a picture of this upper sum and lower sum. You can see that. And by putting in the similar manner, the way you calculated fx is equal to x, you can calculate this one also. But this example is important. So we have this example, one of the example. Fx is defined by 1 when x belongs to, this is defined on the 0b. So when x is rational in 0b, it is 1. When x is 0 in 0, when x is irrational, then fx is defined by 0. So find whether fx is Darbo integrable on 0b or not. If yes, then find the integral. B is greater than 0. So we take the partition of 0b, and we know that there are infinitely many rational and irrational on a subinterval by density theorem on any subinterval. So this function takes 1 when x is rational. This function takes 0 when x is irrational. So in this, by definition of the function, we can see that fx has only 2 values in any subinterval, either 0 or 1. So in this way, you can clearly observe that the supremum of the function on any subinterval 1 for every k, and it will infimum for every k, it will be 0, because there are infinitely many, for any subinterval, rational, irrational both points are there. So we can easily observe that these values are coming. So upper sum we will define by this formula. So upper sum will be coming out 1 times b minus 0, that is b only. And lower sum will be coming out infimum times length of subinterval. So infimum is 0, 0 times this length of subinterval. So that is 0. Now you see that b is not 0. B is strictly greater than 0. So upper sum, its sum strictly greater than 0. So infimum of the upper sum will be nothing but b itself, and the supremum of the lower sum will be 0 itself. So you see that upper integral is b and lower integral is lower Darbo integral is 0. Both are not same, so f is not Darbo integrable. Now you see that this function is bounded, but it is not Darbo integrable. You can see. Okay. So now there are some results we have to see. So this is a small result. So if we have a function which is bounded on AB, if P and Q are partition of AB such that P is subset of Q, then this result holds. So this result basically I have already explained by picture, but this is a mathematical version of those pictures. So what is the meaning of this picture? This result, you can see that P is a subset of Q, and P and Q both are partition. That means Q is the partition that contains more point than the partition P. So that means in this, Q is a superset of Q. So Q must contain the more point than P. So if we introduce more point in the partition, what will happen to upper sum and lower sum? So if we introduce more point in the partition, so basically here Q contains more point. So if we introduce more point in the partition, lower sum corresponding to P, it will be less than or equal to lower sum corresponding to Q. So Q contains more point than P. That means lower sum decreases. Lower sum increases. So Q has more point. So corresponding to Q, lower sum is bigger than corresponding to P. So you see that lower sum increases. Again, you see that upper sum corresponding to Q is less than or equal to upper sum corresponding to P. You have seen this result already via picture. What is happening when we introduce new points in the partition? What is the impact of new points on the lower sum and upper sum? We have seen already. So we can prove it mathematically also. So I'm not going into detailed proof of this result. Now we can see again by this picture. You see that symmetrically. This is the lower sum. So now suppose this is my P corresponding to P and this is my Q. Q contains, suppose for the single point U, this is Q. Q is nothing but P union extra point U. So U is a single point which we are introducing and calling it Q. So you can see that corresponding to U, if we draw the rectangle, then we get extra area. And you see that in this way, the lower sum will increase. By picture itself, you can see that lower sum will increase corresponding to Q. And in this picture, you see that when we introduce this point U, then corresponding to this point U, when we draw the rectangle, we will get this extra area will be removed. That means upper sum will be decreased. So this is the geometrical aspect. We can immediately conclude this result by looking at the picture, although we can prove it mathematically also. Now this result is also important. If f is bounded function on AB and P and Q are partition of AB, then lower sum corresponding to the partition P is less than or equal to lower sum corresponding to the partition Q. Yes, someone raised hand. Any question? So what do you mean by this result? This result says that you choose any arbitrary partition. P and Q are different partition. We don't know whether P is contained in Q or Q is contained in Q. These two are different, completely disjoint. This might be completely disjoint partition also. P and Q are any arbitrary partition of AB. Then what is happening to the lower sum and upper sum? Lower sum is always going to be less than or equal to upper sum, no matter what partition you choose of AB. So this can also be proved. So simple result. I'm not going to prove it. So now this result is again, we have seen already intuitively. Lower integral is always going to be less than or equal to upper integral. This can be proved also by simple results. So these are basically simple proof. Okay. Okay. Any other doubt in this thing? Okay, then I'll move to the next. So we have seen that Darbo integrability and Darbo integral, how we define Darbo integral. So first of all, we define Darbo upper sum, Darbo lower sum, then Darbo integral exists, Darbo why Darbo integral exists, because Darbo upper integral, Darbo lower integral exists. Based on the previous knowledge of the real analysis, we see by using completeness property, we saw the existence of all these lower integral and upper integral. Now there is another version of integrability criteria, that is Cauchy criteria for the integrability. Let's see what is this. This is also important while we prove the results for the many function. So let's see. A bounded function f on AB is integrable if and only for every epsilon positive there exists a partition P of AB such that upper sum minus lower sum is less than epsilon. So difference between upper sum and lower sum is less than epsilon. So this is one of the important results for the solving problems. Again, I'm not going to prove. Maybe proof is very simple actually. Sorry for the noises coming from the background. Proof is again very simple. Okay, so I'm not going to other things. So let's see what else. Now here comes the Riemann definition of the integrability. So far we have seen the Darbo integrability. Now we will see what is the definition given by the Riemann. Okay, so let's see. Let f be a bounded function on closed interval AB, and let P be the partition of AB. A Riemann sum, Riemann defined a sum that is called Riemann sum of f associated with the partition P. It is sum given by this form. Summation k equal to 1 to n f of xk times tk minus 1, where xk is any member from this subinterval tk minus 1 tk. So now you see the picture. What is the difference and what is the similarity between this definition of Riemann integrability and Darbo definition of the integrability? So you see that if we take the partition, so t equal to a and t equal to t equal to b, and we take suppose x1, x2. So between x1 and x2, we pick any arbitrary point t1. So sorry, x1. Between a and t1, there is a point x1. Corresponding to x1, there is f of x1. Sorry for the noises. And for the point x2, you see that corresponding point f of x2. So f of x1 and f of x2. And similarly, tk minus 1 and tk, you see that this xk. So what is the difference between basically? Okay, let me just, I'll come because maybe this noise coming from just behind. I'll just take it. Just wait, please. Okay, sorry, this is some public noise. I can't avoid. Anyways. Okay. Am I audible?
Yes, ma'am. Yes, ma'am.
Okay, so let's go back to the Riemann definition of integrability. So here, what is the different thing and what is the similarity? You see the definition. Here we are taking f of xk instead of taking any supremum or infimum. So basically f of xk, what is the f of xk? It is the height corresponding to xk. Xk is any point in the subinterval tk minus 1 and tk. And what is f of xk? F of xk is the height basically. So it is an arbitrary height. So you can pick any arbitrary height, construct your rectangle and calculate the area. So Riemann does not bother about the lower height or upper height. He took any arbitrary height by taking any arbitrary point in the subinterval tk minus 1 and tk, and corresponding to that point he took any arbitrary height. So f of xk is any arbitrary height because f of xk denotes the ordinate and it represents the any arbitrary height. So you see that there are infinitely many Riemann sums corresponding to particular, for a particular function you can construct, there are infinitely many Riemann sums. But in the Darbo integral it is not happening. That is basically based on the infimum and supremum height, so lowest height and highest height, but this is something different, we are getting it. So you see that f of xk, so you can just check in the picture corresponding to x1. X1 can be here, x1 can be anywhere. So if I pick my x1, x1 can be here, x1 can be here, f of x1 can be here, this line can be here, this line f of x1. So x1 can be anywhere and corresponding f of x1 can be anywhere. This is not fixed. So f of x1 is any arbitrary height. In the similarly, f of xk is also any arbitrary. Xk is any arbitrary point between tk minus 1 and tk. So corresponding height is again any arbitrary height. The choice of xk is quite arbitrary. So there are infinitely many Riemann sums associated with single function and partition. So now based on this Riemann sum, how we define Riemann integrable function? Let's see. The function f is Riemann integrable on AB if there exists a real number r such that for every epsilon positive, there exists a delta positive such that mod of s minus r is less than epsilon for all Riemann sum of f associated with a partition P having mesh P is less than delta, where this s is given by this. Basically, this mesh P I have not defined earlier. So this mesh P is nothing but the maximum of the subinterval, maximum of the length of the subinterval. So this number r is the Riemann integral of the function, and it is denoted by r a to b f r. So basically, you see that what is happening here. So there are infinitely many choices for the Riemann sum. So if we are able to find a real number R such that we can approximate that real number R to this Riemann sum. So there are so many Riemann sums, infinitely many choices for the Riemann sum S. So many choices. So many Riemann sums we have. And if there is a fixed number, real number R, such that we can approximate all those Riemann sums to this number R, then we say that this number is small r, that is called Riemann integral of the function f on AB. And mathematically, we approximate all the Riemann sum by R by this. So it has been observed that a bounded function f on AB is Riemann integrable if and only if it is Darbo integrable, in which case value of the integral agree. So basically this theorem gives an insight. Both definitions agree and both are equivalent. Riemann integrability criteria and Darbo integrability criteria both are same. So that's why basically we call it Riemann integration. We don't call it again and again Darbo integral, and we both are same. So I'm not going to prove it, but you should know that both definitions are same, and you can also prove it mathematically, of course. So you see that Darbo integrability criteria and Riemann integrability criteria are same. So now there are some properties of the Riemann integral that is more important. So one property is that every monotonic function f on AB is integrable. So every monotonic function, if function is increasing on closed interval AB, it will be integrable. If function is decreasing on closed interval AB, it will be integrable. But what about the converse? You have to think. So if function is integrable, is it necessary it has to be monotonic on some closed interval? You have to think of some example. If converse is true, if converse is not true, whatever is happening, you have to think. Okay. Every continuous, next result is that every continuous function f on closed interval is integrable. Okay. So if any function which is continuous on a closed interval, that is going to be integrable. And we know that every continuous function which is continuous on a closed interval, that is also uniform continuous function. So we can see that every uniformly continuous function is integrable. But what about the converse? Every integrable function is always continuous, and because continuity comes with many things. So suppose a function is like, I will just go to that topic again. So this is one of the result. Okay. Okay, so now let me go to the next thing again. L6, L7. Okay. This is another property. I will go to quickly. If f and g be integrable, then scalar multiple of that function is also integrable, and sum of the integrable function is integrable. So you can think of some vector space linear algebra thing here. Just try to think of that something like, if I collect all the integrable function, then with this thing, scalar multiplication and vector addition, is it going to be a vector space or not? You can think of that thing also. Okay, I'm not doing the proof. Proof is very lengthy. Okay, so this was, let me go to the next thing. Monotonicity of integral. Actually, there are so many things I cannot cover in 2 hours. So I'm just going through all those things quickly. So if f and g are integrable function on closed interval such that fx is less than or equal to gx, then corresponding integral will follow the same thing. This is called monotonicity of integral. So this is also a useful result in order to calculate the integral of some function which is related in this way. X is less than or equal to gx, then corresponding integral follow the same thing. This one is again one of the important result. If function f is integrable on AB, then absolute value of f is also integrable, mod f is integrable, and the value of the integral of mod of integral is less than or equal to integral of mod. Now the question is that if mod f is integrable, then f will be integrable or not. So I'm not going to proof it again. Proof is very lengthy again. So what is the converse? Converse is not true. So if mod f is integrable, then f may or may not be integrable. We can see this example. Function f from 0 to n to r. We says that fx is equal to 1 when x is rational, when fx is equal to -1 if x is not rational. So the lower sum will be -1 and upper sum will be 1. So f is not integrable, you see, but when you define the mod of f, it will be 1 throughout, so it will be integrable. So now this is one of the example when mod f is integrable but f is not integrable. And another property of integral is domain additive theorem, that is called domain additive theorem. This has been used many times in the school time, you have seen that. So if f is a function on AB and A is less than C is less than B, and f is integrable on AC and CB, then f is integrable on AB, and the integral of f AB can be written as A to C plus C to B. So now you see that this you have used many times in the school time. So integral of f from A to B can be written as A to C plus C to B. This is called domain additive theorem. Okay, so I'm just going to the important results, not all the results. Okay, one of the important aspect is that fundamental theorem of the calculus in the Riemann integration. So if G is continuous function on the closed interval AB, that is differentiable on open interval. If G dash is integrable on AB, then integral of G dash from A to B is given by GB minus GA. This is called fundamental theorem of calculus version 1. And there are very beautiful application of this theorem. I will also discuss some examples. So, and this is the version 2, fundamental theorem of calculus 2, calculus the version 2. If f is integrable function on closed interval for any x in closed interval, capital F is defined by e to x ft dt, then this integral function f is continuous on closed interval, and if small f is continuous at some point x naught in open interval AB, then capital F is differentiable at x naught, and the derivative of capital F at x naught is given by f of x naught. This is very, very important version. Basically, this is very popular version. So you can just, so let's see how to apply these theorems while doing some problem solving thing. So I'm not going to the proof. So we can see the questions like this. This question. Calculate the limit x goes to 0, 1 by x, 0 to x, e raised to power t square dt. So these kind of questions many times you can see in JAM exam also, or MSc entrance or something. So these questions looks complicated, but these same questions are very simple when you know the fundamental theorem. So you see how to, let's see how to solve such kind of problem. So first of all, focus on the function. So this is my problem, okay? So limit x goes to 0, 1 by x, 0 to x, e raised to power t square dt. So we have to consider our main function, which need to be integrated. So e raised to power t square. So this is my function. Consider a function f on r such that f of t is equal to e raised to power t square. Now we just, because domain is not clear here, so I just consider on r, okay? Until unless we see any problem. So observe that this f of t is integrable. Then we define this by using the fundamental theorem of calculus. We define this integral f of x, capital F of x, 0 to x, e raised to power t square dt. Now we see that this is my small f. This is my small f, and we define the integral of this function by capital F of x. So this small f is continuous at 0. Therefore, by fundamental theorem of version 2, capital F, the integral function, is differentiable at 0, and the value of the function at 0, f dash 0 is equal to f of 0, that is equal to 1. So we have f dash 0 is equal to 1. So now by using the definition of the derivative at 0, we can write limit x goes to 0, f of x minus f of 0 divided by x minus 0, it is equal to 1, and x is not 0. So we can just put the value of capital Fx. Limit x goes to 0. What is the capital F of x? That is 1 x minus 0. So 1 by x times 0 to x ft dt minus 0 to 0 ft dt is equal to 1. So it will give you limit x goes to 0, 1 by x, 0 to x e raised to t square dt, it is equal to 1. So value of the integral such that limit x goes to 0, 1 by x, 0 to x e raised to t square dt equal to 1. So this value is nothing but 1. In the similar way, if we have to calculate this one, we can calculate this one also by considering e raised to power t square. So I hope it is clear what you did. You just whenever you see such kind of problem, you recognize, you just take this as f of t and check whether this function is integrable. If this function is integrable, define the integrable function and then check the continuity of this function at some point. So this function is continuous at 0. Therefore, by applying fundamental theorem of calculus version 2, the integral function is differentiable at 0 and the derivative of that function is given by this, and apply the writing the fundamental definition for the derivative. Limit x goes to 0, f of x minus f of 0 divided by x minus 0, it is equal to 1. Putting all these value, we'll get this value is equal to 1. So now see this problem, how to do this one. Next problem is like this. So limit h goes to 0, 1 by h, 3 to 3 plus h e raised to t square. This is a similar problem actually in the same different way. So my function is f of p is equal to e raised to t square, and we'll just let 3 plus h is equal to x, then h will be x minus 3. Whenever h goes to 0, that means x goes to 3, and we define the integral function like this: 3 to x e raised to t square. This is my small ft, which is continuous at x is equal to 3. Then capital X, the integral function will be differentiable, and the derivative of this will looks like this: f dash 3 equal to f3 will be equal to e raised to power 9. And then again apply the definition of the derivative at 3. This is the definition of derivative at 3. Just putting all these definitions, and then again putting the value of capital Fx minus capital F of 3. This thing you will get. So this value is nothing but e raised to power 9. Okay. So let's see what next. This kind of problems also can be done. Suppose we are given this a small function denoted by small ft, that is 0 when t is less than 0. This is t between 0 to 1, and that is for when t is greater than 1. Then we have to define the integral function for this function based on this is basically purely the application of fundamental theorem of calculus. So capital F of x is equal to 0 to x ft dt. Sketch capital F, the integral function, and you have to check where f is continuous at which point, and at which point capital F is differentiable. If it is differentiable, we have to calculate the derivative. So this function is given first of all. So we just draw this function, small ft. Now you can observe that this small ft is integrable, and we define the integral function. So we can calculate for fx is equal to g. For t is equal to 0, what is the function? So for t is less than 0, ft is given by 0. Between 0 to 1, it is given by t, and for bigger than 1, it is given by 4. So based on the definition of small ft, we will calculate the integral to capital F. So for 0, for t is less than 0, it is 0. Between 0 to 1, you just apply the definition of integral 0 to x ft dt. So what is ft between 0 to 1? So 0 to x, 0 to 1 you have to define. Okay, so you just put t here, t square. So this value will be x square by 2. And for t bigger than 1, you can write 0 to x ft what will be the value? 0 to 1 and 1 to x. By domain additive theorem we can do it. So now 0 to 1 it is t, and 1 to x bigger than 1 it is 4. So we put the value and calculate the integral. So this comes out to be 4x minus 7 by 2. This integral function turns out to be this thing. Now by looking at this function we can immediately observe that at which point it is continuous, at which point it is not, and at which point it is differentiable. So these things are the simple problem. You can just this problem you can also do by using the fundamental theorem of calculus. Let f be a continuous function on R. We define capital F of x minus 1 to x plus 1 ft dt for all x. Show that capital F is differentiable on R. Compute the derivative. So for some time this question has been asked in examination, like what is the derivative of capital F. So you can just apply the fundamental theorem of calculus and you can calculate. So first of all, what is your function? Given that integral function capital Fx x minus 1 to x plus 1 ft dt. So for any real number e, by domain additive theorem, you can just write it down like that. A to x plus 1 minus a to x minus 1 ft dt. And now this is integral function. A to x plus 1 is nothing but, so let us call it f1 at x plus 1 and let us call it f1 at x minus 1. So now this is a sum of two integral function. So where f1 is this integral function. X can be anything, like here x is x plus 1, here x is x minus 1. So now because a small f is continuous on R, so fundamental theorem of calculus 2, f1 is differentiable on R. And f1 is differentiable at x minus 1 and x plus 1 both. So derivative of the function f1 at both point exists. And because so difference will also be differentiable and the derivative of the difference will also exist. So similarly, so f dash x also exists, and then f dash x will be nothing but f1 dash at x plus 1 minus f1 dash at x minus 1. So by fundamental theorem, it will be definitely equal to f1 dash at x plus 1 is nothing but f small f at x plus 1 minus a small f at x minus 1, because small f, so capital F was the integral function of small f. You see that this one, here it is. So this is the, let f be a continuous function on R. Define capital Gx 0 to sin x ft dt, so that G is differentiable, and compute G dash. So how to compute G dash? Again, it can be done by using the fundamental theorem of calculus. So we consider this integral function first of all, capital Fx 0 to x ft dt. Now small f, what is the condition in the question? Is small f be continuous function on R? So we can define this integral function. So small f is continuous on R. Then by fundamental theorem, capital F, the integral function, is differentiable on R. Now we define for this function Gx is equal to sin x. Then Gx, we know that Gx is differentiable on R. So hence this integral function which is given in the question 0 to sin x ft dt, this is nothing but the integral function of sin x by definition. So basically this is f of gx, and basically this is a composition of f and g. So this is f of g at x. So now you see that capital F, that was the integral function of a small f, small g nothing but the sin x. The composition, both are differentiable on R, so composition will also be differentiable, but that composition at x is nothing but capital Gx, so capital Gx will also be differentiable. And by fundamental theorem of calculus, so g dash x will be equal to f of g dash x. By chain rule, we'll get the result f dash at gx times g dash x. F dash at gx by fundamental theorem will be nothing but small f at gx, and g dash x is nothing but cos x itself. So you see that g dash x will be equal to f of sin x times gx. Now the next simple question is that if small f is continuous on a closed interval such that f of x is greater than or equal to 0 for every x in the domain AB, so that integral is 0. If integral is 0, then fx is also 0 for all x in AB. So such kind of questions can be asked in interview, or maybe sometimes it also comes in entrance and BHM or something like that. So f is continuous function and fx is greater than or equal to 0. So that if integral is 0, then what can you say about the function f? Okay. So condition is given, function is continuous and it is greater than or equal to 0. And what is the additional information we have? If integral fx dx is 0, then fx will be 0 for every x in that. So we just prove it by using the contrapositive argument. If fx is not 0, if fx is not 0, so what is the given condition? Fx is 0 for all x in AB. So if fx is not 0, then there exists some point in the interval AB for which fx is not 0. Then integral will also be not 0. Then we are proving in that way. So you see that if fx is not 0, then what will happen? We'll show that this integral will also be not 0. So I'm not going to prove. You can just try this proof by using contrapositive argument. Okay, these problems. Okay, let me see if I have something else. Okay, some exercise problems are there. Let me just check it. Okay, this problem is very important. This one. You can use it as a tool. So, if f is a bounded function on AB closed interval, there is a sequence of un and ln of upper and lower sum of f such that limit un minus ln is equal to 0, then so that f is integrable, and integral of function is given by limit un and limit n. Sometime whenever you calculate un and upper, un and ln, that is upper Darbo sum and lower Darbo sum. Just you have seen in the example f of x is equal to x and f of x is equal to x square. The value of upper sum and lower sum was coming in terms of n, 1 by n. Something was there, 1 by n is square. So in terms of sequence, if you are getting the value of un and ln, then you can calculate the limit un and limit ln. Whenever these two limits are same, then function is integrable, and the value of integral of f will be equal to the limit of un and ln. So this is one of the trick, one of the formula. This exercise question, this problem, you can use as a trick. Suppose you calculated some un, you calculated some ln. It turns out to be in terms of some sequence. You just find out the limit of the sequence. If it turns out to be same, then function will be integrable and value of the integral will be the limit of the sequence. So like this, you can use as a tool. For example, you see that in example number 1, while we calculated this fx is equal to x square, you don't need to calculate all the things. So you found that upper sum and lower sum, right? So upper sum was b cube divided by 3, 1 plus 1 by n plus 2 plus 1 by n, and lower sum was b cube by 3, 1 minus 1 by n times 2 minus 1 by n. So you just calculate the limit of these two. So limit of upper sum turns out to be b cube by 3 and limit of lower sum turns out to be b cube by 3. Both are same. So that means function is integrable and value of the integral is nothing but b cube by 3. So this one is the quite simple trick for calculating the integral, Darbo integral of any function. Now this example is again important. This problem. If f is integrable on AB, suppose g is a function on AB such that gx is equal to fx except for the finitely many points, so that g is integrable on closed interval AB, and integral of g is equal to integral of f. So basically, I'm not going to prove what is the insight of this example and what is the further extension of this example. It gives you that if a function is discontinuous at finitely many points, then function is Riemann integrable. You have seen that one result is that every continuous function is Riemann integrable, right? But what if there is some discontinuity? So there is a result, you can prove that result by using this problem, that if there is a finitely many points at which function is not continuous, then still function can be Riemann integrable. You can just prove it by using this result. So there are different books. I'm using this book. You can use different books in which proof might be similar or something. So these are the results. Let me just, what are the, okay. This is same. Okay, this is one of the another interesting problem. So that this mod of integration minus 2 pi to 2 pi x square sine raised to power 8 of e raised to power x dx, it is less than or equal to 16 pi cube divided by 3. So there are some complicated integral for which we may not calculate the exact value, but we can approximate, we can find some upper bound for that integral. So my function is that, what is my function? X square sine raised to power 8 of e raised to power x. So this is my function. For all domain we are picking up this minus 2 pi to 2 pi. Observe that fx is a continuous function on this. So we have seen in the property that every continuous function is integrable. So this function will also be integrable. So f is integrable on this subinterval. So because in the question it is talking about the mod of the integral. So if f is integrable, then mod f is also integrable. And what is the value of the mod of integral a to b f? It is less than or equal to integral of mod. So mod of integral minus 2 pi to 2 pi, this value is given by, it is less than or equal to this result we are using here, this result. So mod of this integral is less than or equal to integral of mod. Now you see that this is a trigonometrical function, sine, cos function. This can be easily approximated by sum upper bound. So this is bounded by 1. So this is less than or equal to minus 2 pi to 2 pi and x square times 1. So now we can easily integrate this x square function. The integral is x cubed by 3 from minus 2 pi to 2 pi, and the value is 16 pi cube by 3. So now you can see that mod of minus 2 pi to 2 pi x square sine raised to power 8 e raised to power x dx. This integral is a bit complicated, but this can be approximated by this value 16 pi cube by 3. So this is a very nice problem. We can see in this. So now the next question is simple question. People ask that if a function f is integrable, then what can you say about the square of f? So proof is a bit lengthy, but if f is integrable, then square of the function will also be a Riemann integrable. This has been proved. And what about the converse part? So this part is important. If f is integrable, then f square is also integrable. Converse part is that f square is integrable does not imply that f is integrable. You can see this example. This is fx takes 1 when x is rational, fx takes minus 1 when x is irrational. So f is not integrable. We have already seen that. But what is the square function? Square function is 1. So this square function is integrable. The next example is that if f and g both are integrable, then what can you say about the maximum of f and g, minimum of f and g, and product fg? So if f and g both are integrable function, then product fg, max of f comma g, and minimum of f comma g, these three things are integrable. So what is the hint? Product can be written as f plus g whole square minus f minus g whole square divided by 4. Now we know that f and g integrable, then f plus g. By algebra of integrable function, f plus g also integrable. Now we have also seen that square of function also integrable. So f plus g integrable, then square of f plus g also integrable. Similarly, f minus g integrable, square of f minus g integrable. Difference will be integrable. So this f into g will be integrable. Again, max of fg is defined by f plus g plus mod of f minus g divided by 2. So fg integrable, mod f minus g integrable, mod f minus g integrable. This whole thing will be integrable. So max function will be integrable and min function will also be integrable. Okay, I'm going through the important problems, not all. So just okay, so I think I'm done. So let me just discuss few things verbally. So like there are few things. If function f is continuous, then f is Riemann integrable, right? If function f is monotonic, then f is Riemann integrable. You must think the converse part of all these statements. One thing is that if try to find out if function is not continuous at single point. Suppose I have a function like this. Suppose fx is this, fx is equal to 1. If x is equal to x belongs to 0 to half, maybe, and no, just let me think. Something, some function which is not continuous, you can think of. Okay, suppose alpha 1. If it is alpha 1, when x belongs to 0 to half, and it is 0. Alpha 1 is any real number. If it is 0, when x is equal to half. Maybe some function is like this, or union half to 1. Maybe SA. Exactly, you can think of some function which is, some function is like this. Suppose this is alpha 1, and at this point when x is half, then maybe I'm taking, when x is half, this function is 0. So something like this, or something like this. Maybe if I'm taking this 2, so, and I'm taking alpha 1 is less than 2, so here my alpha 1 and here it is 2, so this function value is 2 when x is half, and all other part 0 to 1, it is alpha 1. So what can you say about how to calculate the integral of this kind of function? This function will be integrable or not? So this function is discontinuous at some point, at single point. So there are finitely many points at which function is not continuous. Then what can you say about that function? So you need to think of these questions. First of all, try to calculate the upper integral and lower integral of a function which is discontinuous at single point. Then take 2 points at which function is not continuous. Take finitely many points and try to find out their function is integrable or not. Then result turns out to be that function is not continuous at finitely many points, then still function is Riemann integrable. Then what can you say about it if there are uncountable points at which function is discontinuous? And what are the limitations of the Riemann integration? Suppose you have seen that the Dirichlet function that is bounded, but is still that is bounded but not Riemann integrable. So that is one of the example which gives you an example that every bounded function might not be Riemann integrable. So these are the things what you have to think. You have to think this thing, and then you can think what are the limitations of Riemann integrable. There are some limitations of Riemann integrable where Riemann integral condition fails, like if some function is not bounded. So here we assume that function was bounded throughout the discussion. So suppose some function is not bounded, can we calculate the Riemann integral of that function? Try for these things, take some unbounded function and try to calculate the Riemann integral of that function. Is it failing or is it working or what is happening? Just look at those things. So if it is failing, then what can be done? So if audience, if there are a student from the masters, then you can think that you must have seen that there are some functions which are not Riemann integrable but Lebesgue integrable. So for the limitations of the Riemann integrable, from the limitations of the Riemann integrable functions, we can jump to the next extension of the integrable functions, like Riemann integrable function to the Lebesgue integrable functions. So yeah, that's all. Yeah. Okay, so I think I'm done. Any doubt, any question?
Hello, sir. Hello, ma'am. Thank you, ma'am, for this wonderful session. You have explained very clearly with figures, and it helps me a lot to visualize the problems. Thank you, ma'am.
Dia, please introduce yourself.
Yeah. Ma'am, I am Diya Shah from West Bengal. I am in my MSc second year. I am doing my MSc from IIT Bhubaneswar.
Thank you, ma'am, for the interactive session and the informative session also. Your session helped us a lot to learn about the Riemann.
Good evening, ma'am. I am Shikha from Birla Institute of Technology, a second year MSc student. Ma'am, your session was really nice, wonderful. Ma'am, the way you have explained the concept using the graphs and figures, it was really very much helpful for us. Thank you, ma'am, for this session. And thank you, Vinod, sir, for organizing such sessions. Thank you.
Thank you, Shikha. Yes.
I'm Gayatri. I have done my graduation from Miranda House College, Delhi. The class was really nice, ma'am, and the notes that you prepared was really useful, and it helps us to understand the concept more. And thank you so much for taking a wonderful class for us. Thank you.
Hi, sir. Myself, Zaira Rumesa. I'm from TMG College, Tirur. And thank you, ma'am, for this wonderful section. Really helpful for us. And thank you, sir, for conducting this section.
My name is Aparna Lal. I'm a graduate student. And ma'am, today's class was very wonderful. I really liked it. The way you explained everything, I just got the concepts. And thank you so much for spending your valuable time with us. Thank you, ma'am.
Thank you, Aparna.
Arya, you
Hi
can
everyone.
continue. Yes,
Hi
Arya.
everyone. I am Anjana from 𝐾𝐬𝐩𝐢𝐫𝐚 Government College, Calicut. I am a member from
Yes.
group Brahmagupta. First of all, I would like to thank Ms. Priyambada Tripathi from University of Delhi for this wonderful session. The session was so helpful and helped us to understand the topic Riemann integration is clearly. Again, thank you, ma'am, for this session, and thank you, Vinod sir and Max Aspirants.
Okay, thank you, Anjana.
Hi, ma'am. My name is Arya. I'm from third year BSc Maths student from Kerala. First of all, thank you, ma'am, for this wonderful section. And you explained the concept very clearly, and it's very helpful to us. And thank you, ma'am.
Thank you, Arya.
Hello.
Yes.
Hello.
Yeah, Nishita.
Hello. Hello, sir. Hello, ma'am. I'm Nishita Pendharkar from TYBSc Mathematics student from Maharashtra. And today's session was very exciting and helpful to us. I'm very thankful to you. Also, the new thing was till today, I was thinking that differentiation came first, as it was taught first. So today's lecture was really very helpful for me, and I'm very thankful to you and also to Vinod sir for conducting this session. And thank you.
Hi.
Yes, Hiba.
Hello, ma'am. I'm Hiba. I'm a first year MSc student from IIT Palakkad. Ma'am, the class was very informative and very nice. The way you have explained everything was so good. Your graphs, everything made us the topic very clear. Thank you, Vinod sir and Priyambada ma'am, for this nice session.
Thank you.
Thank you, Hiba. Others?
I think no one has any doubt.
Hello, ma'am. I'm
Yes.
Malvika, third year BSc Maths student of 𝐰𝐢𝐭𝐡 College, Kerala. Thank you, ma'am, for this wonderful session. It is really helpful for us. Thank you so much, ma'am, for sharing your valuable time with us. I would also like to thank Vinod sir for conducting such a wonderful session for us. Thank you, ma'am and sir.
Thank you, Malavika. Yes, others?
Hello, sir. Hi, ma'am.
Yes.
I'm Andresa Sebastian from Assumption College, Kerala. Today's session was really nice. It was very clear. The presentation was also nice. Thank you, ma'am, for helping us. Thank you, sir, for conducting the session. Thank you.
Right, sir.
Hello, ma'am.
Yes.
Hello, ma'am. I'm Gopika, Aspirants, Good College, Kerala. Today's session is very nice, and
He explained each and every concept really well. Thank you so much for your time and thank you, Vinod sir, for conducting this session.
Thank you, ma'am, for this wonderful session. Wonderful session on Riemann integration. Very well session, ma'am. Thank you, Vinod sir, also. Thank you, ma'am. Thank you, sir.
So let us wind up here. Thank you.